I'm going to do a couple of coordinate problems converting from rectangular to polar and to spherical. And I'm going to start out with a simple problem to illustrate it and then do one slightly more difficult. One of the points I ought to make is try not to rely too heavily on the conversion formulas. Use them, but when you can use angle relationships that you know, that would be better. So I'm going to start out with rectangular coordinates 1, 1, 0. So I'm picking a point that's in the xy plane, 1, 1, 0. And now I'd like to do it in polar form. Well, for polar, I want r, which is the distance in the xy plane, the length of this vector, the xy plane. Theta, the angle formed off of the x-axis by this vector, and then z. I'm just going to take my z. So in this case, well, for polar coordinates, I know that the length of that is going to be 1 squared plus 1 squared square rooted, so it's going to be the square root of 2. So rather than just giving an x and a y coordinate, I'm giving the length. The second one, well, given the coordinates 1, 1, this is pi over 4. And then finally, the last one is just my z coordinate. I don't need to compute anything. Okay? Now going ahead to spherical coordinates, I'm going to have rho, which is the length of the vector in 3 space, not projected into the xy plane. Theta, the same angle as I had in polar form, and then I'm going to come up with a new angle, and that's the angle formed off of the positive z-axis by this vector. So let's see if we can figure this out. Well, rho is just x squared plus y squared plus z squared, the Pythagorean theorem in 3 space, and that's, since this is in the xy plane anyway, it's still square root of 2. The second one was pi over 4, it's theta again, and the last one, well, let's see. I can use my conversion formula, but why would I do that? I could see that the angle formed, so this is my phi here, the angle formed coming off of the positive z-axis is pi over 2. And there I go. Now let's do a second one that's a slightly more difficult, but not that much more difficult. Again, it's one I'd like to do without using the conversion formula. So here's my x, y, and z axes, and I'm interested in the rectangular point 0, 1, 2. So let's see, that's going to be, change my color here, 0, 1, 2. So here's the point in 3 space, and it looks like it's in this YZ plane. So in polar form, well, in polar form, in the XY plane, it's simply 1. That's the length of the vector in the XY plane. And the angle is the angle formed from the y-axis off of the x-axis, and that's going to be pi over 2. So this particular vector, if I project it down into the xy plane, sweeps out an angle of pi over 2. And the last one is simply the z-coordinate, which is 2. So that's pretty simple. Now let's do spherical coordinates. Make that green. So for my spherical coordinates, I want to start out with rho. And rho is the length of this vector in 3 space. The distance of the point from the pole or the origin. Well, that's going to be 0 squared plus 1 squared plus 2 squared, or the square root of 5. The second one is simply theta again, so that's going to be pi over 2. So all I've done is replaced my square root of x squared plus y squared with square root of x squared plus y squared plus z squared, the same angle off of the x-axis in the xy plane. And now what about my third one here? Well, I'm interested in this. What is this angle here coming off of the z-axis? Well, I'm going to redraw this here. So I know this has a length of square root of 2. I know that this is square root of 5, and this is 2. So what is this angle here? Well, it looks like it's the inverse cosine of 2 over the square root of 5. Inverse cosine of 2 over the square root of 5. And I could use my calculator if I want to approximate that, but I'm going to stay with this exact answer. And now I'm finished. I have my answer in rectangular form, polar form, and spherical form. Notice I didn't just pop down put these into the formulas, but I sort of used my diagrams and I thought about the relationships here. Okay, hope that helps a little bit.